Good morning, class. Today we dive into the fascinating work of thermodynamics and specifically exploring efficiency limits and the concept of the Carnot cycle and try to solve two problems about Carnot cycle. Imagine that we have a heat engine, a device that converts thermal energy into a mechanical work. Our goal is to study the maximum possible efficiency of such an engine. Understanding the efficiency limits of the Carnot cycle is critical for engineers and scientists. This helps us develop more efficient systems and pushing the boundaries of what is possible. And let's talk about Carnot cycle and what is this. At first, the Carnot cycle has three main stages. The first stage, called heat source, it's an important stage of the Carnot cycle where a heat is obtained. And the second stage is work execution, a stage where thermal energy is converted into mechanical work. And the final third is heat rejection, the final stage of the cycle where some heat is rejected from the system. And with three stages of Carnot cycle, we also have three limitations of efficiency. The first is the second law of thermodynamics. According to the second law of thermodynamics, efficiency can never be 100%. And the second limitation is called Carnot effect. Carnot effect established a limitation on the efficiency of all heat engines. And the final, third limitation called maximum efficiency. The maximum efficiency of heat engines is only achieved in the Carnot cycle. Now that we understand what Carnot cycles are, I want to show you two problems about the topic Carnot cycle. And the first problem, Carnot cycle and irreversibility. Consider a Carnot engine operating between a high temperature reservoir at 800 Kelvin and a low temperature reservoir at 400 Kelvin. During one cycle, the engine absorbs 2400 joules of heat from the high temperature reservoir. However, due irreversibilities, only 60% of this heat is converted into useful work. Determine the efficiency of the Carnot engine and the total entropy change during one cycle. Let's solve this in the desk. Okay. At first, we have two temperatures, hot and cold. Let's see. Okay. The hot temperature is 400 kelvins and the cold is 400 kelvins. We also have during one cycle the engine absorbs 2400 joules. It's Q hot equal to 2400 joules. And however, due to irreversibilities, only 60% of this heat is converted into useful work, and the efficiency, actual efficiency, is 60%, or we can write this like 0.6. And what we need to find is the efficiency, theoretical, and its total entropy changes during one cycle, which marked as delta S. Next. At first, we need to find theoretical efficiency. And how we find this? We just use this formula. Efficiency equal 1 minus 2 T hot divided by T cold divided by T hot. And we have numbers 400 kelvins divided by 800 equal 1 minus 0.5, which is equal to 0.5 or 50%. There is theoretical efficiency. And what we need to find next, it's the total entropy. Total entropy. And the formula to find this is Q hat divided by Q cold minus T hat divided by T cold. As first, to find the total entropy, we need to find this Q cold. How we find this? We just need, okay. We know this formula where Q cold is work useful minus Q hot. And we also need to find this for useful work. And this formula is to Q hat divided by actual efficiency, which is 60% or 0.5. I read 0.5. Oh, not. There is 1,440 joules. And next we have this and put here. So, oh, no, it's not correct. I'm sorry. Q at the point for useful. And it's 2,400 minus 1,440 joules equal to 960 joules. We find Q cold and put it here. Okay. It's 2,400. Take. Так. Oh, I'm sorry. I had a mistake in the formula. My bad. The actual formula is Q hat divided by T hat minus Q cold divided by T cold. Am I correct? Yes, it's a final formula. Yes. We put the meanings where there is a 2400 and T hat, we know it's a 800 kelvins. And also Q cold we just found. On here. Does it see? Where it is? No. 960 divided by 400. Okay. What we get? The final answer, there is, it will be 3. Here, 2.4. 3 minus 2.4, we have 0.6. So, the total entropy of one cycle, there is 50%, we find, and total entropy is 0.6 to kelvins. Okay, the first problem is solved. Okay, the second problem, Carnot refrigerator. About Carnot refrigerator. Okay. Consider a Carnot refrigerator that operates between a low temperature reservoir at 250 kelvins and high temperature reservoir at 500 kelvins. The refrigerator is required to remove 3000 joules of heat from the low temperature reservoir. Determine the amount of work done by the refrigerator and the total entropy change during one cycle. Okay. Okay, let's solve this. Just what we have two reservoirs. The first is the low temperature, which I mark as T cold, 250 kelvins, and high temperature reservoir is T hot, 500 kelvins, and the refrigerator is required to remove 3000 joules from the low temperature reservoir, which means Q cold is 3000 joules. And we need to find amount of work done by the refrigerator, the work, and the total entropy. To find the work done by the refrigerator, we need to use the formula where we just Q cold умноженное на efficiency. And to find efficiency, what we do, we use the next formula, 1 minus divided, or 1 minus low temperature reservoir divided by high temperature reservoir. And we have the meanings of this T cold and T hot. We just put there here and just solve. There is 1 minus 250 divided by 500, and the total answer is 0.5. 0.5 or 50% is efficiency. and I'm sorry, we put this efficiency here and just find the work done by the refrigerator. Work is equal. We have the Q cold, it's the 3000 joules. Just put them here. 3000 умножен на 0.5. The answer is 105,000 joules. Okay, we found work. And we need to find total entropy. Like in the we need to use the formula where ratio of Q hat divided by 2 T hat minus Q cold divided by T cold. Okay, we have to mix of this T hot and T cold. Also, we have the Q cold. We just need to find this Q hot. So to find this, we use the formula where Q hot is equal to work done by a refrigerator plus Q cold. So the answer is 4,500 joules. Okay, we find this and just put this there here. So 4,500 divided by 500 minus, am I correct? Here and 500 here, and we have Q cold. There is 3,000 divided by what we have 250 joules. Okay, and there is no other space, and just I need to clear here. Right. Fine. To 4,500 divided by 500, we took 9 minus 3,000 divided by 250 is 12. So we get minus 3 to divided by Kelvin. But it's a total entropy, so we just просто убираем минус спереди. Получается, and the answer of the total entropy of one cycle is 3 joule divided by Kelvin. So the answer just with the work we have is entropy -1 3 joule divided by Kelvin, and the work is 1,500 joules. Problem, just solve it. Now that we have solved two problems, I will finish my lesson because of time limits. It's 20 minutes. In conclusion, I want to say the Carnot cycle is an important concept that describes the limitations of efficiency and thermodynamics, and the principles of the Carnot cycle find wide application in various practical systems. Through challenging problems and solutions, we grappled with the intricacies of calculating efficiency, work done, and entropy change in Carnot engines and refrigerators. As we close this lesson, let's carry forward the knowledge gained about the Carnot cycle and its role in defining the boundary of efficiency. See you again.